now we go into turbulence kinetic energy and turbulence intensity. And we did talk a bit about this in the previous slides. Now, we did recall that from basic physics, kinetic energy is calculated using the following equation. Kinetic energy equals to half mv squared, where m is mass and v is velocity. But in meteorology, we often use specific kinetic energy, means that we don't consider the mass. We assume the mass to be constant, and energy that we calculate using this formula here is per mass, means joules per kg. So when we do that, we can ignore the mass. So that's why it's called the kinetic energy per unit mass, or the specific kinetic energy. Now, by extension, we can focus on just the portion of specific kinetic energy concerning the turbulent fluctuations only, namely the turbulence kinetic energy, or I think turbulent kinetic energy. So there's two parts to it of this kinetic energy. One is the mean kinetic energy, and the other is the turbulent kinetic energy. And this, they just focus on the turbulent component of it. So instead of using mean V, we use here U prime average square and V prime average square, and so on. So this prime indicates turbulence instead of mean, like before. Then you just simply add them all up, divide by 2, and you get the specific turbulent kinetic energy. Or if you want to use the variance, it's also the same as this U prime average. So this equation and this equation is the same. Like just now, we calculated that sigma U is 0.15, so you can imagine the value you put inside this sigma U is just 0.15 divided by, if you have this, you just add them all up, then divide by 2, and you should get the turbulent kinetic energy that deals with just the turbulent component of the kinetic energy of the air flow. For laminar flow, which contains no microscale motions, the turbulent kinetic energy is equal to 0. Does that make sense? It does, because in laminar flow, there's no turbulence. There could be flow, there could be velocity, and the velocity could be high, but then the variations of velocity within that flow is very small. Or when we get the average of all the variations, we see that the turbulent kinetic energy is just 0 in laminar flow. So even though, it says here again, even though U, V, W are not necessarily 0, the turbulent kinetic energy can be 0 for laminar flow. Larger values of TKE indicate a greater intensity of the microscale turbulence. So another new term here, microscale. The turbulence that we deal here is the microscale version of turbulence in the flow.